Okay, thank you for coming. It's a pleasure to be here. I always feel that little bit misfit. I'm just a musician in the kind of developer conference. I'm the developer in the musical conference. So I'm always like this kind of misfit and interdisciplinary researcher. So I wanted to talk to you today about great opportunities of data and when using music, technical challenges, also different applications, show you some old-fashioned videos of different applications that I have contributed to, and make you think a little bit about the impact that our algorithms have on people and how we can make sure that we are aware of this impact and we can somehow also change or modify the impact we want to have. Just for those that have never worked on music domain, music is a great domain to work and to develop. It's the best. It's always, for me, I like music since I was born. I listen to music a lot. I also played music as an amateur, but I was more maybe because I didn't want to play all the time and repeat the same things. I decided to code and do music with computers. So music offers many opportunities to create applications that many people will use because all of us listen to music. Music is also related to our feelings, to our culture, and also accompanies us even in therapy or at the end of our lives. And music is not only a great area of research, but it's also an amazing technological area of challenges. Just if you think about music pieces, the concept of songs, we say there's one song for every heart. There's more songs that have been composed than people in the world. Not only that, but people create also their versions, their covers, songs. So there's a huge quantity of data. This data is mostly audio data, so it's acoustic signals. It's time temperate in time. So it's amazing how much you can learn from this kind of data. That's also has created a lot of industry interest to develop platforms that can facilitate the access to music data by providing recommendations, search capacities, or retrieval scenarios. So this is where I have worked in my career. I have tried to develop algorithms that make sense of all this music data. Not only is there are different music songs or there may a lot of music material, but music data is also not only audio, it's multimodal. There's you can find audio, you can find video that is represented. You find also musical scores, which is kind of symbolic information, which you find lyrics and also perception of people around music. So it's also a challenge how to access this data. I wanted to play you a first video of a project that we did some time ago about trying to build an online tool, a web-based tool that allows us to visualize all the information we can have from one single piece, which is a music symphony. It's the Beethoven Eroica Third, where we had, like, for instance, in this performance by Concertgebouw Orchestra in Amsterdam, we had like 70 audio tracks, 8 video tracks, score, text, gesture, physiological data, and so on. So just a very old-fashioned video to give you an idea of all the information So just to show you this video. Okay, so I guess you have seen how complex can be one single piece. I mean, there is a lot of information. We had troubles also finding tools that are ready to deal with this complexity, also especially for classical music, and can also allow you to build things upon this. In this case, we built several applications for people to enjoy a concert before, during, and after the concert. So I wanted to explain you how this field has evolved a bit. When I started and my career, maybe when I was a student, there was the starting of all these music platforms, and people were trying to say, okay, how can we access music? And the first thing we thought was about manual tagging, and this is maybe, if you are familiar with other field, is the same. So we wanted to incorporate knowledge from musical experts about music, and then several companies such as Pandora is a music recommendation engine that is still working in the US, or allmusic.com, which incorporates very good information about music. This is an example maybe of a song of Shirley Horn, and then you have biography on and all this expert information that you curate and put it in the repertoire or in the platform. Of course, this became soon very problematic because it was scalable. It was not scalable enough, like to hire people, of course, to do all this manual expert labeling. So, of course, we try to understand how people would describe music. For instance, if we listen to music, how we perceive melodies, instruments, or chords, and how to teach our computers or how to develop algorithms having this same procedures, or trying to somehow describe music in the same way. And I put here the definition of algorithm. Of course, you may know what algorithm is, but the idea was to try to automate a little bit expert knowledge and try to extract, in my case, I was focusing on audio signals, try to extract meaningful information from that using knowledge. We're using knowledge that developers we had. For instance, many developers in this field do have some musical background, so they know about music, about scales, about how different notes are related in frequency. Developers also know a lot about audio signal processing and acoustics and how to extract information on the acoustic features. And then also, some of the developers also had a knowledge about music perception and cognition neuroscience. So this was an interdisciplinary field where people coming from different backgrounds try to address what we call the semantic gap, which is how to go from the low-level information, which is audio, text, video features, to more high-level knowledge, so information to knowledge. And this is what we are trying to reach since the very beginning of the last century now, so, or the century, but already for 20 years or 25 years. So trying to somehow know more about music while developing computational tools. So this is more or less the same. Of course, we were a little bit the people in the middle of computer science, musicology, and neuroscience. So there was a first community, or a community of people that are now around this International Society for Music Information Retrieval, which I had the honor to be president a few years ago, and has been increasing also the industrial interest, because there are many big tech now that are working in the music industry. So you see here maybe some sponsors we have for a conference. And if you're interested, we have our next conference in autumn in India, in Bengaluru. No, in December, sorry. And now the call for paper is open, so you are welcome to attend. There's also virtual attendance possible. So this is how we evaluated at the beginning our algorithms. Okay, we had music, we try to describe, we try to apply some description of some algorithms. Then we have people annotating music, and then we try to somehow contrast how people and how algorithms would describe music using accuracy metrics that might be very similar to some of the tasks that you work on, precision recall, errors, and so on. And then we had some knowledge about our algorithms, how it worked. So in this sense, I developed or contributed to different technologies. One, for instance, is Melodia. Melodia is a plugin for Sonic Annotator. It's an audio editor where it was developed in C++, and it tried to extract from audio. For instance, if you have an audio file like this, a song. There was something inside of you. So you try to extract just the melody or the pitch. Okay, this seems an easy task, but it's quite kind of difficult because we can just focus on one, but when you have different voices, it's very difficult to extract. And this software called Melodia, we have many people downloading in the first years, and many people building applications. I guess you have not seen some application where you can visualize your voice when you're singing, or you can search by humming. You can say, I want Twinkle, Twinkle, Little Star, and then it will get it from your data set. So this is the kind of algorithm that we developed back in some few years ago. I also worked a lot with tonality, trying to extract, for instance, from the audio, the chords that are played. It's also a very common application. There's even companies like Chordify that tries to extract chord information so that you can play with a guitar or you can transcribe for musicological purposes. And I developed also an HPCP, which is another plugin which tries to extract this kind of C major chord. And if you see, this is a little bit the kind of algorithms that we developed. We had in the top, we have like, so you see audio signals, and then spectral sinusite extraction, spectral whitening. This is trying to emulate our ear and how we perceive the sound and how we extract this. And then you had this kind of more knowledge-based kind of block diagram. So we really could control all the steps of the process. We knew what was failing, and we could try to evaluate very well. And we could control a lot our system. We were somehow experts in dominating our machine or somehow our algorithms. I also work a little bit on rhythm. Rhythm is trying to instead of looking for periodicity in the frequency, or you try to look for periodicity in the audio. And this is an example, for instance, of beat tracking, which is also very well-known application. It's just trying to track the beat. For some music, like electronic music, is easy. For some, like classical music, is much more difficult. So I was also, and you see also the same. We estimate period, tracking, selection, and so on. This is kind of block diagrams we had for our systems. Of course, we started to incorporate machine learning in this pipeline. Of course, we had data. We have some annotations for evaluation. We try to apply also learning strategies from these annotations. For instance, can I maybe have my algorithm learning about the range of pitch of certain voices, or can I adapt my architecture just to fit a little bit with the material or with the context? And we started to incorporate supervised learning. I'm not sure if you are familiar with machine learning, but supervised learning is trying to algorithms that learn from annotated data. So you need somehow to first create annotations, like there in the top. In this case, I put the example of emotion. For instance, you have music, and then you ask people to annotate, is it a happy song? Is it a sad song? And then you have also categorical, like positive emotion or sadness, and also dimensional. Dimensional is arousal, is more like the energy of the song, and then valence is positive and negative emotions. So this is a way to annotate emotions. And when you have all these annotations, you train machine learning algorithms that learn from the features or from the descriptors we abstract, for instance, from melody, tempo, or all these aspects that we have heard. And then it train a model, and then you have new data it can classify according to this trained model. So supervised learning, I was using that and contributing to supervised learning for different tasks in music. For instance, an important task is instrument classification. You hear a song, and then you want to say it's a band, or it's an orchestra, or it's a voice. This is also very good for retrieval, for classify music in large collection. I was also working in emotion a lot. I will show a demo later. Also, style, for instance, we can classify flamenco versus pop versus rock, and this is also good for music platforms. They can create playlists. They can also organize and recommend music based on your playlist. And we also did a project which is called, this is because I'm moving a lot, or maybe I should keep it more quiet, where we try to somehow classify your preference. So we try to model, this was called the musical avatar. We analyzed, this is maybe my earrings. So we were trying to analyze, for instance, if you give me all the music that you like, I will just tell you what you like. I model your preference, and then I can just recommend. And we did it also visually. It's very old-fashioned, but we try to put, for instance, this is my musical avatar. I like acoustic guitar. I also like this very tonal music, and I'm a little bit sad, you know. So this is what we try to do. So I will play now a video about a very early system. It's from Cyril Laurier. His PhD thesis in 2011 that tries to classify mood in music by means of lyrics and also audio features.
Ne me quitte pas, il faut oublier.
Bonita mañana, bonito lugar, bonita la cama.
Por la mañana yo me levanto y voy corriendo desde mi cama.
Okay, so you have seen a little bit how those algorithms work. You know, I was saying all these guys super modern will see my UX. The UX is a bit old-fashioned, but it's a great work also by Cyril Laurier. He has now a company also where they do live visualization of music, but you see those are really cultural concepts that are emotion, and then they are quite well modeled. Music and emotion is one of the applications we use a lot for marketing. When you go to a store or or you have the music to make you go faster or eat faster or just be okay. And when you go to the dentist, then you are more relaxed. So it's the kind of application industry also is using a lot for also engaging with people emotions. So I wanted to tell you a little bit how the story went. I mean, we were like developing algorithms and we incorporated machine learning, and all of a sudden we started using deep learning because, of course, if it was working much better when you had a lot of data and you have a lot of annotations. Of course, annotations in music are very expensive, so you don't have huge annotations like, for instance, in image, where you can ask people to, but in music, you have to listen to the song, you have to, and there's a lot of subjectivity, so there's not much data, but still people were using neural nets, and then we started to go, okay, now we don't need more features, you know, the people working on features were somehow like, we don't need you, you know, we can just get the audio and learn to get the data with APIs. We get data, and then we train. We don't need features anymore. So the idea is that we just needed computing and data, and you cannot see how insane an amount of data and energy is used to train those models for music. I mean, which is really not something saving lives, but of course we were going back away from knowledge. And developers didn't know anymore what were the models, how they were working. They were just trying brute force to apply models that were designed for images, for speech, and then trying to a little bit train them and change parameters and then do grid search and see, but it's also expensive to train so many times your model. So we had the impression that the knowledge was not exploited at the end because you could just be training or dealing with music or with anything else. So we started the era as we go from network design. For instance, this is one of the algorithms we developed in the last year where we just, you see, okay, this deep nets. I mean, there's no more acoustics, no more musical knowledge there. There's only kernel sizes and filters and layers. So several architectures when then maybe complemented with knowledge-based approach, which is the current status where you try to go back to knowledge-based approaches to try to get rid of this complex network architecture. But you know, all this huge amount of data allows us to outperform the glass ceiling and also to improve our tasks. Of course, we never more understand what they are doing. I mean, we just know they work, but we don't really know how. And we are trying now to study how they do it, but we were only reproducing. And there is a very good history about, I don't know if anyone has heard about the clever hands. Has anyone knows about the clever hands effect? So there was clever hand was a horse in Germany that was really doing mathematical operations. You know, I mean, he could predict dates, he could just sum, multiply, and everyone was really, because you give an input and the output was great, you know. And then they tried. There was a committee of 13 people, a vet, a mathematician. They were trying to make him fail, you know, but they couldn't. And at the end, they realized that he was not even doing computation. He was just following his master behavior, and then he could predict a bit the outcome. So many of the systems were shown to be a clever or horse, and we say there is a horse is a system that is actually addressing the problem it seems to address. So maybe even if we give you it's a happy song, it really doesn't understand. Maybe it's just checking the frequency number 3, or it's just checking long songs are correlated. So correlation and causality are not the same. So we had this kind of black box models that really are not doing what we want to do. So we discovered then we are not really advancing on the knowledge gap, but of course the algorithms work better. There is, of course, a difference in motivations from the more scientific side of artificial intelligence, where you try to somehow learn about human intelligence and try to emulate this and try to compute to the more engineering side of deep learning, where you are so lazy, you just give data and then train. So, of course, this is a very, very simplified, but this is a little bit what I'm trying to work on that. And still, there are many challenges that now we are addressing, because human and machines are different. For instance, people have individual opinions about music. They don't all agree that this music is happy or sad. They also may have cultural difference. So machines have always majority views. So there is this bias to majority. So then if you are a minority and you like certain kind of music, you will never be well recommended or would recommended by these systems. Also, people use a priori knowledge they have and a priori exposure to music when they listen to music. While machine learning, you need to retrain from scratch. And people also can learn models for melody, and then they can apply to mood, but machines are, the computational tasks were somehow separated. And people also can be asked to explain why they think this song is sad. And those models that are also very complex are kind of black box, so it's difficult to know why they are classified like this. And also you have biases, and machines do also have biases because they learn it from the data or from the algorithm. So these are somehow the research topics we are currently addressing on those in music and data. For instance, personalization, how to train models maybe for the average, and then you use active learning and then try to maybe switch or change it a little bit according to your taste, or this kind of zero-shot learning, or high combining not deep learning with traditional classifiers, so this more symbolic and deep learning. Also the idea of multitask learning, then how to explain those models. And I guess this is finally very broad to the machine learning community. In music is also the case. We are trying to work on these topics. But in any case, we are aware that those models are not perfect. They are not always working well, but we use them a lot in practical applications. And I'm sure you all listen to music in music platforms, so you have be recommended music, and you have maybe followed those recommendations. You all access YouTube platforms, see your recommendations. So I will not talk about this kind of applications. I will give you some other examples of things we can do with this kind of music and data. First one is a project where we let me first it's a project where we developed in the video we saw at the beginning a music app, like it was a tablet app where you could access information about the concert before, during, and after the concert. And you could also, depending on your user profile, if you are a musical expert or you don't know anything about music, this was for classical music, you could have different kind of information about music. For instance, some people that are not very, very experts, they want to know, okay, which is the bassoon? I mean, where's the bassoon and when it plays. So we were trying to show different instruments playing, and then some other people want to follow the scores, or more musicologist people, they want to see where they are in the score. It was also a very very demanded feature was to, okay, how long will it take, So people are, of course, I mean, how I am in the middle, I'm at the end, so we just incorporated this structure analysis and see, especially for symphonic pieces, it's difficult to see and to understand. And we also did some, the experimentation with the gestures of the conductor. So I will show you a video now of one concert that we did few years ago, where we tried to do this in real time, and which is also challenging because those algorithms have latency, and then you want to visualize, so you need to analyze audio and then display video. So all of this is a very, very complicated latency, especially in real time. And this is one of the concerts we did. Okay, so we were able to experiment with different ways of visualizing music, and also how people may have different interests in music visualization. For instance, some people just want to go to the concert, they just want to listen, and some other people might want to have this kind of. This was for young people, so it was also in an educational context. Another application or another field where I have worked a lot is in flamenco singing. Alexandra also mentioned before, I'm working with a singer who is teaching flamenco, and also in the context of COVID, she's teaching a lot online. And then we try to develop some technological tools for learning flamenco with audio and also with visualization flamenco. It's an oral tradition, so they are not musical scores. So it's very difficult for people to read it. So, and especially there are a lot of ornaments like mordents or this kind of trills that they are not notated, and also it's very difficult to visualize. So these kind of things, it can be up or down, and all of this we did. So I will just play you the trailer of the but it's in Spanish, so some of you will not get it, but you will learn. You will hear in the background the nice voices of the singers that I have worked with.
¿Puede la tecnología ser el camino para aprender cante flamenco? El Grupo de Tecnología Musical de la Universitat Pompeu Fabra colabora con otros investigadores e instituciones para estudiar el cante flamenco desde un punto de vista tecnológico. Investiga cómo modelos computacionales y matemáticos son capaces de ayudar a analizar, sintetizar y caracterizar la música flamenca. En nuestra investigación, desarrollamos las herramientas necesarias para la descripción automática de piezas flamencas en cuanto a melodía, armonía, timbre y ritmo, y para la caracterización expresiva del cante flamenco. En este MOOC, la cantadora y profesora Alba Guerrero nos enseñará los estilos del flamenco y sus recursos vocales, juntamente con Emilia Gómez, doctora e investigadora de la Universitat Pompeu Fabra, que nos mostrará el enfoque más tecnológico del cante flamenco, analizando la voz a través de 3 parámetros fundamentales: el volumen, la línea melódica y el timbre.
Un mantón cruza en el pecho, los zarcillos de mi madre, cantamos toda la noche, ya hasta que amanezca el día, cada vez que voy a Huelva, siento una gran alegría.
Okay, so this is another example of the kind of ways you can use it for teaching, for learning. It's more and more people are using data for tracking, for instance, the rehearsal practice, which are the parts of a piece that are also more difficult to play. We also developed something similar using synthesis of singing, not only analysis for choir singers, that you can also see if you play well. And then I think I will skip this video because we are, no, it's okay, I can play it. This is the last project where I work. We try to build an app. It's called Cantamos, it's in Latin, cantamos.app, I think. And it's about a tool for choir singers, especially in the pandemic where they could not rehearse physically. You will hear synthetic voices, so it's not real people, it's just deep learning-based singing.
Gonna lay down my sword and shield down by the riverside, down by the riverside, down by the riverside. Gonna lay down my sword and shield down by the riverside. Gonna study war no more, study war no more. I ain't gonna study war no more. Ain't gonna study war no more. I ain't gonna study war no more, no more. I ain't gonna study war. Ain't gonna study war no more. Ain't gonna study war no more. I'm gonna lay down my sword and shield down by the riverside.
Okay, this project got a lot of track during COVID because we were able to build a virtual choir with people from different countries trying to rehearse together and sing together with this kind of technologies. And finally, maybe one project I liked a lot, which is about music therapy. It was one project where we tried to build a personalized music, and we found a lot of bias of current algorithms to young people. So we had to restart from scratch our model to train it for music from seniors. So it was also very challenging. And you can build your own application. So there are many ideas. We developed all the algorithms that I have presented today are in the open source library for audio and music description. In Essentia, it's a C++ library optimized for computational speed. It also incorporates Python bindings for fast prototyping. Incorporates both this feature structure and also machine learning. So we integrated with TensorFlow, and this is a huge effort by many people in the music technology group trying to contribute to a common repository of algorithms that you can integrate in all applications. Finally, I want to end a little bit my 5 minutes left with social impact that those technologies, which is the topic of my current research since the last 2 years. And the fact is that this kind of music and algorithms that I have been developed and myself and all the community are having a huge impact on the opinion that we have about music. Also, they somehow decide what are we going to listen to, they recommend it, and they also, you have seen, can induce us or some emotions or affect our emotional well-being. So I started a project at the Joint Research Center in Seville, where we try to see which is the social impact of AI, not beyond music, also in other domains, and trying to discuss a bit how can we do, how can we make sure our algorithms are designed in a way that are somehow according to our values and are used according to our values. For instance, algorithms reinforce a lot gender bias. For instance, algorithms learn from data different gender bias that are present in the data, for instance, music platforms, and they also propagate them when they train algorithms. So we did a study on how music platforms are really not democratizing the access to music. They're always reproducing same bias that we had according, for instance, to gender. Algorithms are also culturally bounded. So most of these algorithms work very well for Western mainstream popular music, but then they don't work at all for other cultures. For instance, they don't work with flamenco, they don't work with classical music because they are not so commercial. So we need to make sure that our algorithms really preserve cultural diversity so that my algorithm can work for Indian music or Turkish music. So this is now a topic of research, and that's why also the conference is shifting between continents to make sure we represent everyone. And finally, also those algorithms can now emulate a lot of tasks that musicians were doing in the past. So we also have to think about how this will affect the music business and also musicians. For instance, those recommender systems can also generate music, and then they don't have to pay to artists and creators. So it's also an issue how those algorithms can really replace people and how responsible we are. So I'm currently trying to address this through the whole life cycle of algorithms. How can we ensure that our algorithms are evaluated not only in terms of accuracy, but also in terms of aspects such as bias and fairness, transparency, societal and environmental well-being, which is very important when we train large models. And finally, how can we also assess this as developers when we create a system? Because as you may know, even if we think technology is neutral, it is not. So be aware that even if you have a very low level coding task, you will probably have a social impact. So just to end up, if you're interested in this kind of topics, I have two openings now. One for PhD in the area of artificial intelligence in music creation, how to address transparency and originality of those music, try to analyze. And the second one is broader, is more on recommender systems in the context of the European Commission Digital Services Act, how to define methodologies for transparency and documentation so that we really know how those systems are working and how they are recommending music. So this is all from my side. I hope you find it interesting and you will enjoy maybe working in the future with music data. Thanks a lot.
I'm sorry, I don't really know what to say because I just really enjoyed the presentation on so many levels. So I have a question actually for the audience. We have 1 minute left until we technically have to kick her off the stage, but I have so many questions here from the audience. So should we at least go through 2 of them? Yes?
Yeah,
all right.
I'm sorry I talked too much. I put too many videos, I think.
Well, I saw everybody enjoying themselves. So I'm going to get through these, some of these. But so I'm going to start out with the question number 6 here. And it says, how close are we to generate music to please the music taste of the created classifiers? So I think it's like the people. Who wrote that question? All right.
Yes.
Yell it out to me. I'll try to repeat it.
Hello? Okay.
So please the taste of who? Because it depends on who you want to please.
Because it seems that we are also creating the classifiers that decide about what is the musical taste. What should we recommend? So it was about how close are we from creating the music that will start to fulfill the needs of the algorithms.
Yeah,
and maybe we can skip the humans in the whole system.
We are very close. Very close. There's the level of realism of AI generated music is very high. Of course, music as an art is subjective. So you may always, people were at the beginning scared about MP3 because it was not very good quality, and now everyone listen into MP3 or into mobile phone, no? So it's also subjective, but yeah, we are close of being able to produce personalized music and compose it, but over personalization can be also dangerous because if you only listen to your music that you like, you get into a bubble, and at the end you are polarized somehow. So technical possibility there is of creating music, and of course now we have to review all the aspects of authorship and copyright, because if you are training on data, this data might be composed by someone, so this someone is providing the music material that you are using for training. So I don't know if I replied, but we are very close. Especially the most difficult instrument is singing, and they are very, very good singer synthesizers now.
Thank you.
And I think this kind of goes on to one of the other questions that we have here. So you can elaborate on it if you wish. So the question directly asks, what is your opinion about on AI systems which are trying to make and compose music? And you kind of touched on it a little bit.
I think it's a tool that many people are using for creative purpose. So it's like yet another tool. I mean, many composers use now computational tools to create, to get inspired. So I think we have to be aware of how we use it. So, but yes, it will have an impact on the music we listen to. I don't know if you will want to, I think about maybe this kind of handmade clothes, so you will have handmade music and then not handmade industrial music. So I think we will have to inform people. And this is about the topic of transparency, how to make them aware if they are listening to real music or to synthetic one.
Okay, and so I'm going to take a chance for one last question, and the rest we'll have to do in the interview that we're going to do with you later. It says, you've illustrated, you've done some illustrations with Western music. So how do the models translate to other music cultures of the world? For example, music from India and such. I think it was maybe referring to the mood cloud.
Yeah, in any case, we cannot make global models for all musical cultures. So we need to build models that are applied to different cultures, for instance, to different languages. So we need to make context-aware models that really learn, because there's no overall emotion. And even in emotion, there's a lot of personalization. So we need to really build personalized models. So in the case of Indian music, for instance, or in flamenco, you need to restart your training a little bit and consider how people will annotate here, or how people will perceive emotions. So all is the same if you develop a tool for left-handed or for right-handed, and then you take it and you use it with your left hand, it doesn't work, no? So it's the same. If you develop it for Western, then it won't work for other cultures.
So maybe it comes back to that principle of also, which a lot of people have touched on, which is like bringing in people from different, who have different lenses to contribute to the models that you're implementing.
Yes, the more diversity, maybe the better your model is. But of course, you cannot never please everyone. So maybe bunch of personalized model or context-aware models, I think it's more efficient than trying to build one model that fits all.
Okay. Well, we have lots of other questions. We're going to have to ask you to cover them. We're going to do an interview with you in the cloakroom. So just want to say thank you on behalf of JOTB. Can we all give Emilia Gómez a big round of applause?
Yeah, thank you. I will be around, so if anyone is interested in music and tech, just come to talk to me. Thanks.